everyone, I'm Yuxiong He from Snowflake AI Research. I'm excited to introduce Arctic Inference, our open source system for high-performance generative AI model serving. This is joint work with an amazing team, and I'm presenting on behalf of all of us. Inference systems are the bridge between models and real-world applications. They determine speed, scalability, and cost. But most systems force a trade-off, optimize for responsiveness or throughput, really both. Arctic Inference break this compromise. It delivers responsiveness, great generation speed, and cost efficiency all in a single deployment, built for enterprise scale and open to the community. In this talk, I'll show how we make it possible to excel on both speed and cost. To understand why Arctic Inference is different, let's first look at the three key matrices that matter in production-grade inference. First is responsiveness. This is about time to first token. In interactive applications like chat, search, or agentic workflows, latency during prefill directly impact the user experience. Second, generation speed. So once the model starts generating, we care about token throughput. This matters in long responses, streaming, or step-by-step reasoning. Third, cost efficiency. Inference at scale can be expensive. We want to maximize useful throughput per GPU to keep costs down. Now the challenge is, most systems cannot achieve all three at once. Some are fast to respond, but don't scale well. Others are efficient in batch, but lack for real-time use. So in production, teams often run multiple systems, one for low latency use and another for high throughput. That create the increase on the complexity and cost. This triangle of trade-off is not unique to AI. It's like what we saw in the auto industry as well. For years, we had to choose between speed, efficiency, or affordability until electric vehicles changed the game. Arctic Inference is our attempt to do the same for the AI inference. In the triangle chart here, you can see each open source system falls short on at least one metric. Only Arctic Inference reaches the outer frontier, delivering responsiveness, fast generation, and cost efficiency in one unified system. Let's now look deeper. So why do these trade-offs exist in the first place? And what architectural innovations allow Arctic to overcome them? First, where are these inference systems forced to make trade-offs? So the root cause lies in parallelism, how systems scale across GPUs. Here there are two common strategies, tensor parallelism and data parallelism. Tensor parallelism split computation for each token across multiple GPUs. This gives great prefill speed and generation speed, since all GPUs work on every step. But it also requires constant coordination, and during that communication, GPUs are idle. So this makes it inefficient under high concurrency or batch traffic, limiting throughput. On the other hand, data parallelism avoids this problem by splitting across requests, not within them. And each GPUs just run independently, so there's no communication overhead, you get high throughput. But because each request runs on a single GPU, it cannot match the latency or generation speed of tensor parallelism. As shown in the radar plot and the table, that tensor parallelism excels at speed but struggles with throughput. Data parallelism delivers high throughput but sacrifices responsiveness. So these limitations are built into the current parallelization strategy and also explains why today's inference system cannot deliver all three matrices at once. In Arctic Inference, we set out to break this trade-off. I'll show you how next. So how can we mitigate this trade-off? A simple thought is, what about we just combine tensor and data parallelism and switch between them to get the best of both worlds? Unfortunately, that doesn't work. So these two approaches, tensor and data parallelism, use incompatible KV cache layout, and switching between them would require costly reshaping, so that wiping out any performance gains. More precisely, the KV cache generated by the attention layer stores key value vectors for reuse during generation. Tensor parallelism split attention head across GPUs, while data parallelism keeps requests isolated, that leading to fundamentally different layouts. To address this, we developed a different form of parallelism called Arctic sequence parallelism. It has three key properties. First, unlike data parallelism, it splits work within a request, so it can leverage multiple GPUs to process the prefill, delivers high prefill speed per request. Second, unlike tensor parallelism, it doesn't split the work per token. That reduces communication latency and allow for higher throughput than tensor parallelism at the expense of lower generation speed. Third, which is also the most important thing, its KV cache layout aligns with tensor parallelism layout by splitting attention across heads. That enables seamless switch between the two. And this KV cache layout compatibility is the foundation for what we call shift parallelism. So shift parallelism is a runtime strategy that dynamically chooses the optimal mode. It uses tensor parallelism for small batches to maximize generation speed, and it uses Arctic sequence parallelism for large batches to maximize prefill speed and throughput. So as shown in the diagram, shift parallelism eliminates this classic trade-off triangle. It delivers high prefill speed, high generation speed, and high throughput, all in a single deployment. The bottom left table here also summarizes similar result, that shift parallelism achieve near perfect performance across all three dimensions. For the full technical details, please check out our paper listed at the bottom of the slide. Now let's take a look at how shift parallelism does compare to tensor and data parallelism under real-world inference traffic. So here the first row shows a request arrival rate over a 2-minute time period with multiple bursty arrival rates. Here, the second and third rows shows that shift parallelism, the blue line, achieve lowest median initial response time and per token generation latency. In fact, compared to tensor parallelism, the gray line, or data parallelism, the black line, it always retains very close to the lower of the two, regardless of the traffic. Final row, it shows that during high traffic, shift parallelism achieve a maximum combined throughput that's 35% better than tensor parallelism and very close to the data parallelism deployment. So what does this result tell us? That this real world benchmark reaffirmed the core advantage of shift parallelism. So it adapts the dynamic traffic and eliminates this traditional latency throughput trade-off, which existing system and parallelism approach cannot achieve. So besides shift parallelism, Arctic Inference also implements multiple state-of-the-art optimizations to improve throughput and latency for real-world enterprise inference. I'll provide a very high-level overview of this here. We have detailed blog posts and papers on each of these, so please check out the QR code if you're interested to learn more. So let's start from throughput optimizations. The first throughput optimization we're looking at is SwiftKV. So here we notice that a large portion of enterprise AI workload spend over 90% of computing prefill. So we developed SwiftKV to identify redundancy in the prefill computation and reduce prefill computation by up to 50% while preserving accuracy. So this brings a throughput improvement of up to 2x. Our next optimization is on embedding model inference. Embedding model inference compresses a significant portion of enterprise AI workloads. However, we observe that the open source implementation like LLM underutilize GPU when running them. We identify the source of the bottleneck and remove them. That allows Arctic Inference to achieve up to 16 times higher throughput than LLM. In addition to the throughput optimizations, Arctic Inference also implements powerful latency optimizations. First of them is speculative decoding, a popular latency optimization based on the observation that token verification is much faster than token generation. We developed two distinct speculators to target different patterns. First is surface decoding for repetitive generation, so common in agentic workflows. Second is lightweight draft models for non-repetitive generation combined with an optimized speculative pipeline. These are unified into a single speculative decoding framework, delivering up to 4 times faster generation in real-world enterprise scenarios compared to the open source LLM. Here we have a short demo of faster generation with Arctic Inference speculative decoding. On the left, we have the baseline without speculative decoding. In the middle, we have speculative decoding for non-repetitive generation using LSTM-based draft model. And on the right, we have surface decoding for repetitive generation. So for the purpose of demoing the impact of surface decoding, we are running the same query for the second time that for the surface decoding case. Now let's play the demo. As you can see, Arctic Inference with a draft model significantly outperforms the baseline in speed. And for repetitive use case on the right, surface decoding is even faster, completing almost instantly. While meanwhile, the baseline is still running. Let me also rerun it once again so you can see once more. Note that surface decoding finish even before the baseline can produce a single token. It shows the power of these inference optimizations. So beyond speculative decoding, Arctic Inference also implements an early termination strategy called Dinosaur to speed up reasoning models. Here is the idea. Reasoning models often overgenerate because they are unsure when to stop. But for easier problems, we can periodically probe the model to check how confident it is. And if the signal is strong enough, we early stop without losing accuracy. So this approach gives us more than 2 times speed up on easy tasks and up to 1.4 times speed up on average. This video is a demo of Dinosaur in action. It shows a reasoning model solving a 2-variable linear equation. On the left, the baseline goes through the full chain of the thought. But on the right, Arctic Inference with Dinosaur steps in, and once the model is confident in answer, it just stops early. So in this case, Dinosaur achieved over 5 times lower latency with no loss in accuracy. So all these pieces we've discussed, shift parallelism, as well as other throughput and latency optimizations, can be combined in Arctic Inference. And when we put them together, you get breakthrough performance for real-world enterprise workload. Take a look at the figure on the right. So for generative AI tasks, Arctic Inference outperforms open source solutions, delivering up to 3.4 times lower latency and 1.7 times higher throughput. These reinforce a key point. While most systems force you to trade off latency and throughput, Arctic Inference delivers both in a single deployment. And for non-generative workload like embedding, the gains are even more dramatic, up to 16 times higher throughput compared with VLM. And these aren't just theoretical results. Arctic Inference is already powering production workload in Snowflake Cortex AI, including our deployment of Llama models. And the chart on the bottom shows benchmark results from artificial analysis comparing response time across cloud providers. So that we can see, as of August 3rd, 2025, the Snowflake endpoint powered by Arctic Inference is among the fastest across the board. And most importantly, it's fully open sourced, free for the community to build, extend, and use. We believe AI becomes more powerful when it's accessible, and our goal is to make fast, responsive, and cost-effective inference available to everyone. Getting started with Arctic Inference is simple. It works as a plugin to VLM. You just install it using pip, and the functionality becomes available directly in your VLM environment. Once you installed, you can just launch with the same familiar VLM serve command, but now enhanced with support for shift parallelism, speculative decoding, swift kiwi, surface decoding, and so on, all configurable through a small number of additional flags. And you don't need to change your models or workflows. Arctic Inference is designed to be drop-in and composable, so you get the performance improvement with minimum friction. We hope you give it a try, and we can't wait to see what the community builds with it. That's my talk today, and thank you.